Yes, good morning everyone. Welcome to Crystal Clear Chemistry channel. In order to crack either JEE mains or NEET exam, let's strengthen our chemistry basics through this channel. In this video, I am going to discuss the part 4 of ionic equilibrium, where we are going to focus more on common ion effect and the salt hydrolysis. Okay, so the theory part of the physical chemistry plays a major role in solving the problems of assertion, reason type or statement type questions and all. So the theory part of the physical chemistry also very important. Let's discuss in detail about the common ion effect and the salt hydrolysis. What is common ion effect? The extent of ionization of a weak electrolyte is decreased by the addition of a strong electrolyte. So, if we consider a weak electrolyte, its ionization or dissociation decreases if we add a strong electrolyte to it which has an ion in common with the weak electrolyte. That means if both have the common ion, definitely the weak electrolyte dissociation decreases. They have given two examples here. Addition of ammonium chloride to the ammonium hydroxide decreases the dissociation of ammonium hydroxide, as ammonium hydroxide is a weak electrolyte. Even the sodium acetate addition leads to the decrease in the dissociation of acetic acid. Let's discuss in detail now. Suppose if we consider the acetic acid is a weak electrolyte. If it dissociates, it gives acetate ion and H plus ion. For this weak electrolyte that is already present in the water, that means the aqueous solution of CHCCOH if we take, and if we add a strong electrolyte like sodium acetate. Sodium acetate is a strong electrolyte and it dissociates into CH3COO minus and Na plus ions. Okay, so what we have done here, we actually increased the concentration of acetate ion by adding the CH3COO. If we consider this equilibrium, the acetic acid dissociation equilibrium, we increased the product in terms of acetate ion so that whenever the system is at equilibrium, if we increase the concentration of a product, then we can say that the equilibrium will shift towards the left. That means the backward reaction takes place to the greater extent. What does it mean? It means that the dissociated ions also associated and forms a weak electrolyte. That means the dissociation of the weak electrolytes is decreased just because of the common ion and according to the Le-Chatelier principle, right? So this is what about the common ion effect. Let's take another example. Suppose if we consider ammonium hydroxide, it dissociates into NH4 plus ion and OH minus ion. It's a weak electrolyte. For this weak electrolyte, we have added let us suppose that we added the second electrolyte we added for the weak electrolyte solution, that is nothing but the ammonium chloride here. When the dissociation of NH4OH is at equilibrium, if we add NH4Cl further, which gives ammonium ion, it means that we are actually increasing the concentration of ammonium ion in that equilibrium. So as soon as the product uh, sorry as soon as the product is increasing here, as soon as the product's concentration is increasing here, definitely the equilibrium according to the Le-Chatelier principle shift towards the left. That means backward reaction takes place. What does it mean? The dissociation is suppressed. The dissociation of NH4OH is suppressed because of the common ion of the strong electrolyte, and this effect is called common ion effect. Okay, this common ion effect we can This principle or this effect is used in preparing the buffer solutions, and this particular common ion effect principle is used in the qualitative analysis of cations and all. More about this we are going to discuss in the case of buffer solutions. Okay, these are the two applications where the common ion effect is involved. Eh, just two examples I have mentioned. There are many applications of the common ion effect that we are going to discuss when we are going to discuss that buffer solutions. Okay, now listen carefully. Suppose if we consider a salt, if it dissolves in water, the in the salt the cation will be there and the anion will be there. If either cation or anion or both, if they react with water, what will happen? And that reaction is called what? First of all, when the salt is dissolved in water, if the cation or anion of the salt or either or both the ions, if they react with water, then that reaction is called hydrolysis. Then that reaction is called hydrolysis. What will happen if they react with water means they may become acidic solution, the solution may become acidic, or it may become basic, or it may become neutral. It is based on the salt that is undergoing the hydrolysis. In fact, it is the reverse reaction of neutralization, right? We know already, like whenever the acid plus base gives rise to acid plus base combined together, it readily forms a salt, and it readily forms water. When the salt is reacting with water, the reverse reaction if we assume, then depending upon the salt, the total resultant mixture may be either acidic or basic. If both are of the same concentrations or same moles, something like that, it may be even neutral. That means that means we cannot say that always the salt water or the aqueous solution of the salt is neutral. It may be neutral, may be acidic, or may be basic, because the ions of the salt are reacting with the water. Okay, now let us say how they react and what type of salts are acidic in nature, what type of salts are basic in nature, and how what type of salts are neutral in nature. Okay, now listen carefully. There are total of three types of hydrolysis: strong acid and weak base salt. If we consider salt of strong acid and weak base, if we consider, for example, strong acid, let's take strong acid HCl. Weak base, let us consider an example NH4OH. The salt of this acid and base is nothing but NH4Cl. So suppose if NH4Cl undergo hydrolysis, let us see what will happen. Similarly, if we consider a weak acid, say CH3COOH, acetic acid, and a strong base, let's consider NaOH. And what is the salt formed here? Sodium acetate, nothing but CH3COONA. If we take the aqueous solution of this sodium acetate, let us see what will happen to the solution, or let us see what will be the solution nature, whether it is acidic or basic or neutral. Similarly, the salt of weak acid versus weak base. The best example is ammonium acetate, CH3COONH4. Ammonium acetate is the salt of weak acid and weak base. Okay. Now let us see one by one what is the nature of the solution formed by the salt after the hydrolysis. First one, the salt of strong acid and weak base. Now listen carefully now. Here if we consider strong acid and weak base salt, ammonium chloride is the best example. When the ammonium chloride is dissolved in water, it readily produces ammonium ion. It readily produces ammonium ion. Here, ammonium ion is going, when it is reacting with water, it readily produces a weak electrolyte like NH4OH. As the NH4OH can dissociate again into NH4 plus and OH minus, there exists equilibrium because NH4OH is a weak electrolyte, and hence in the case of NH4Cl, only the cation will undergo hydrolysis, which is called cationic hydrolysis. Cationic hydrolysis. Due to the reaction of cation of the NH4Cl with water, the resultant solution contains more of H plus ions than the undissociated NH4OH. Right? Just because of the undissociated NH4OH, the basic nature will not, there is no OH minus ions in the solution, as the NH4OH molecules are undissociated. As a result, the solution contains more of H plus ions. If the solution contains more of H plus ions, we can come to know that it is acidic in nature. Understand or not? Now, let us suppose that Kh is the hydrolysis constant. If it is the hydrolysis, I mean, this is called hydrolysis, and whatever the equilibrium exists, whatever the equilibrium constant of this hydrolysis is nothing but hydrolysis constant, which is represented by the letter Kh. And if we write the Kh for this, the Kh is nothing but NH4OH concentration into H plus ion concentration divided by NH4 plus ion concentration. We don't take H2O as it is very high, 55.55. Anyhow, if we take the Kb for the NH4OH, Kb expression for the NH4OH, and if we take the Kw value, that is nothing but H plus ion concentration expression, H plus ion concentration into OH minus ion concentration. If we really simplify by writing all these expressions, you can express the Kw in terms of Kh and Kb. Here the Kw will become Kh into Kb. So in that case, if just like alpha for the dissociation of an acid, for the hydrolysis process, let's degree of dissociation is H, then it is nothing but Kh divided by C, just like that of Ka divided by C for the dissociation of acid. For the dissociation of acid, alpha is equal to, sorry here, just write, let's write alpha is equal to square root of Ka by C for the weak acid dissociation. Similarly, for the salt hydrolysis, if H is the degree of hydrolysis, square root of Kh by C you will get as the expression. Anyhow, these are the resultant expressions which we need to remember to solve the problems. But how we can get the Kh into Kb is equal to Kw? By writing the expressions individually, you can able to draw the relation between Kh and Kb, and that Kh and Kb is nothing but Kw. Okay, now if we apply the negative logarithms for this particular resultant equations, you will get the expressions as pH is equal to half into pKw minus pKb minus log C. Clearly you can see here. How we got that one? With the help of H plus ion concentration. What is H plus ion concentration? It is C alpha. Instead of alpha, we take degree of hydrolysis here. So you can clearly see the pH here, that is nothing but half into pKw minus pKb minus log C. Okay, so the conclusion here is, whenever we take the salt of weak base and the strong acid plus weak base. Salt, if we consider, if the salt is dissolved in water, as it contains more of H plus ions, it is acidic in nature, and that acidic nature solution pH can be calculated with the help of this formula. Okay, so can we quote different examples here? Let's take different examples. Suppose if we consider H2SO4 as the strong acid and weak base. For example, if I take FeOH twice, this is a weak base, and what is the resultant salt here? FeSO4. FeSO4 is the salt of a strong acid and weak base, and it is no doubt it is acidic in nature. After undergoing hydrolysis, the salt produces acidic solution. Okay, so here we can easily remember that if the salt is of strong acid, acidic nature. Similarly, if the salt is of strong base, basic nature. Right? Right? That we are going to discuss now. See here, you can clearly see here. Uh, but before that, I have given example here. You can go through the example. Just by knowing the formula, you can easily substitute the given information. And here they are asking for the degree of hydrolysis small h. You can calculate and you will get the answer as 4.9771. Okay, now let's quickly get into the second case now. The salt of strong base and weak acid. There are many examples you can see here. H2C2O4 is a weak acid, H3PO4 is a weak acid, HCN is a weak acid, and there is salts of strong bases. If we consider, these are all the salts. Just like that of the first case, if we calculate the KH, you can calculate, and it will be the CH square by 1 minus H, and KW expression will be KH into Ka, and OH minus ion concentration also you can calculate. And here what happened, just like that of the first case, if we consider the KCN hydrolysis, for example, KCN on hydrolysis readily produces HCN undissociated, right? HCN undissociated, and K readily converts into KO. Here the KOH. Okay, when as soon as the KCN reacts with H2O, it readily produces undissociated HCN and OH minus ion concentrations. And of course, K plus and OH minus readily produces KOH. And we know if the KOH is present in the water, I mean in any solution in excess amount, you can say it is basic in nature. That's how the strong base and weak acid salt solution is basic in nature. And thereby you can calculate the OH minus ion concentration, and POH you can calculate just by applying the negative logarithm. But here the important point to be noted is in the case of this salt, this time the Cn minus ion is undergoing hydrolysis, is reacting with water. As it is anion, you can say that it is anionic hydrolysis. Anionic hydrolysis. So strong acid strong acid and weak base is undergoing cationic hydrolysis, whereas strong base and weak acid is undergoing anionic hydrolysis. Okay, and you can clearly see how to calculate the POH and then pH for the strong base and the weak acid. Of course, you will have the formula in your book, but all these formula how they have derived means in this way they have derived, right? And what about the third case? It is the salt of weak acid and weak base. salt of strong acid and weak base. You can see here uh, weak acid and weak base if we consider, then can you expect what type of nature the solution will acquire? As both are weak, as both are weak, there is a chance of either cationic hydrolysis or anionic hydrolysis. There is a chance of either cationic hydrolysis or anionic hydrolysis. If they undergo either of these two, then the solution may be acidic or the solution may be basic, right? We have already seen, if it is cationic hydrolysis, what type of nature it is? Acidic in nature. If it is undergoing anionic hydrolysis, the salt solution is basic in nature, just now we have seen. Now if both are weak, it depends, the salt solution nature depends upon Ka and Kb, as they are the weak acids and weak bases. If Ka dominates than Kb, then the solution is acidic in nature. If Kb dominates Ka, then the solution becomes basic in nature. Okay, it all depends upon Ka and Kb values, and hence the Kw will be Kh into Ka into Kb. Both dissociation constant of acid and base we have to take. Depending upon the values only we can come to know what type of the solution it is, and depending upon the pH you can calculate. And pH how to calculate? As Kh is nothing but square root of Kw by Ka into Kb, you can clearly see that the pH expression as half into pKw plus pKa minus pKb. Okay, right. So all these formulae, you list out the formulae and the nature of the salt hydrolysis, then you can easily solve the bits. Okay, right. Just I want to give some conclusion here. So what is the let us see what it is. Let me take a slide here. Right. The conclusions here are, if we consider strong acid plus weak base, weak base salt, salt, or weak acid strong base salt, or if both are weak acid and weak base, and let us check what will happen if we take both strong acid and strong base. Okay, if the salt is of strong acid and a weak base, as acid is strong, the salt also acidic in nature. In this case, as base is strong, the solution is basic in nature. In this case, as both are weak, it depends upon Ka or Kb. Ka greater than Kb acidic, Kb greater than Ka basic in nature, acidic and basic in nature. Then if it is strong acid, if it is of from strong acid and strong base, we can say that the solution is neutral in nature. Understand or not? Next, what type of hydrolysis these salts are undergoing? In the case of acidic salt, it is undergoing cationic hydrolysis. It is undergoing cationic hydrolysis in most of the cases. In the case of basic salt, the basic salts are undergoing anionic hydrolysis. In the case of weak acid or weak base, either it can undergo cationic or it may undergo anionic hydrolysis, purely depending upon the salts purely depending upon the weak acid weak base dissociation constants. Then what about this one, strong acid and the strong base salt? It can neither undergo cationic hydrolysis nor undergo anionic hydrolysis, and hence the result, and hence we can say that the salt of strong acid strong base does not undergo any salt hydrolysis. That is the reason why we discussed only the three cases. Though there are four possibilities, we discussed only three cases because the salt of strong acid strong base does not does not undergo the salt hydrolysis. Okay, this is the conclusion. You should have definitely an idea about the weak acids weak bases, strong acid and strong bases. Then only you will have the idea of the salt hydrolysis. Let me say what are the strong acids, what are the weak bases, and what are the strong acids strong bases and all. Let us see here. Let me take another slide here to revise those uh, substances. Okay, so very important student, just listen here. Let's revise the examples: strong acids, weak acids, strong bases, weak bases. Okay, if we consider the weak acids, H2C2O4 oxalic acid weak acid, HCN is a weak acid, H3PO4 is a weak acid, and if we consider CH3COOH, CH3COOH is a weak acid, H2SC is a weak acid. All these are the weak acids, and even H2CO3 is a weak acid. Try to remember the weak acids. Okay, and what about the strong acids? HCl is a strong acid, H2SO4 is a strong acid, HNO3 is a strong acid, HA is a strong acid. What about weak bases? Weak bases, NH4OH is a weak base, ZnOH twice is a weak base, and similarly AlOH thrice is a weak base, FeOH twice is a weak base, MgOH twice is a weak base. So like this we can quote the weak bases. And what about the strong bases? Strong bases, KOH is a strong base, CSOH is a strong base, NaOH is a strong base. Okay, so all the first group hydroxides are strong bases, and these are all the weak bases. By remembering which are strong and which are weak, you can automatically predict the nature of the solution of the salt if it undergo hydrolysis. Understand or not? Definitely these examples will be helpful for the next concept, buffer solutions. For the buffer solutions also, one must have the idea which are strong, which are weak, either they are acids or bases. Okay, so I hope this video will be really helpful for you. If you really like the video, please like, share and comment. Don't forget to comment, and whether it is helpful for you or not, whether it is helpful for you or not, you just comment. Okay, thank you one and all.